Hello. So we're getting into recursion now. Since we've done the basics in class, I want to continue with some more examples. But first, I want to explain the Ackermann function in a way that was consistent with what we did for the first few examples. So let me define the Ackermann function using notation that we used for the first three examples we did. So here it is. And what's nice about this notation is very easy to translate into code. You can almost copy and paste. So what I'll say is if this function is defined as if m equals 0, then I need to return m plus 1. That's it. So otherwise, if n is 0, then I will return actually a recursive evaluation. So I have to call a again. But on n minus 1, so m gets smaller. But n goes up by 1. Okay. Otherwise, here's where it gets really interesting. I return a of n minus 1, but actually the n that I pass along is itself a recursive evaluation. And here's where really crazy things can happen. Okay, so what I did was I gave this program a main where I can actually input m and n as two command line arguments. So let's explore what this function does. So if I say Ackermann 2, that's 7. Ackermann 2, that's 9. Ackermann 2, 4, that's 11. Doesn't seem to be growing too quick when I have m as 2. But let's see what happens when I make m a little bigger. So m is 3. Okay, 29. 3, 3, 61, 3, 4, 125, 3, 5. Okay. What if I make m 4? So go 4, 2. Huh. Suddenly, I run into some trouble. So if we look at the table of, oh, by the way, you should give money to Wikipedia. I do that every year. So if we look at the table of Ackermann, first, actually, let's check to make sure we got it right. So 2, 6, let's spot check. That should have been 15. We didn't have that on the table. 2, 4 was 11. Yep, I see that. Okay. And then 2, 3 was 9. 3, 3. Did I do 3, 3? Yep, that was 61. And 3, 4 was 125. But something crazy happened when I tried to do 4, even just 4, 2. So it turns out this is just an enormous number, 4, 2. Because what happens is if m starts to grow, you see, in order to decrease m by 1, I make n just a huge number. N grows to be a humongous number. So it takes a while to get that back down. That's the intuition for it. But let me just show you, even just 4, 2. We were looking at 4, 3 in class, which is even bigger. But even just this number, 2 to the 6, 5, 5, 3, 6. It can't do it in C++, but Python is a little smarter with this. Let me just show you what this looks like. So I have to do something a little special even to print this as a decimal number. So, okay, so this number is 2 raised to the 65536 power minus 3. Okay, now it's going to do that, and then it's okay. So here's the number. Look how many digits it has. Well, how many digits does it actually have? Okay, so let me just hack a little bit in Python to get that. Whoops, yeah, so I'm going to do that, .format. Okay, so let's see, how many digits does this have? So Ackermann of 4, 2 has 19, almost 20,000 digits, okay? Ackermann 4, 3 is 2 raised to this enormous number. And that number's so big, you can't even fathom how many digits it has, okay? That's why we need special notation just to represent it. So very interesting. With really simple code, you can make these they call them very large numbers. I mean, they're bigger than anything you would ever encounter in physical reality. I mean, this is way, many orders of magnitude bigger than the number of particles in the universe already. And now you're going to raise 2 to that number? Okay, good luck. So it's interesting. So we stumbled across an area of math called very large numbers. Fine. So it's just interesting that we could do that with such little code. But what's even more interesting about this is this Ackermann function. So it grows very quickly. What it means is its inverse grows very slowly. It grows at a crawl. So, you know, the inverse of this number is 4, 3. Okay, so this is a humongous number. And the output of that function would be 4, 3. Which are 2 pretty small numbers. Okay. So what it turns out, there are certain algorithms that look like they run in constant time. So it seems like they always take the same number of steps. And these are pretty simple algorithms to describe. But what you can show, and I'll talk about this more in 371, is that those algorithms actually theoretically, even though you would never notice a difference between this and a constant, they theoretically have inverse Ackermann runtime. Okay, so we'll talk about that in the spring. But for now, it's just a mathematical curiosity. Okay. But the real point of all this for the purposes of this class right now is I'm trying to show you how to implement recursive functions and the fact that you can have a function that calls itself. It has to have a stopping condition, which means at some point it's going to have to return something that's not just another call of itself. Otherwise, it'll go on forever, and you have infinite recursion. Okay. Now, what we're going to start to do is use recursion to design implementations of different algorithms. Okay. So let me start by looking at a simple example and see how we can write a recursive function to compute what we're after. So you might have seen this before, factorial operation. So 5 to the wow. Okay, so it's factorial. 5 exclamation mark is equal to 5 times 4 times 3 times 2 times 1. Okay, so in general we say n factorial is equal to n times n minus 1 times n minus 2 times ... all the way down to 1. So this is something it's similar to an exponentiation. It's just a little different. So instead of multiplying by the same number every time, you multiply it by 1 less, 1 less, 1 less, 1 less. Okay. I could certainly make a loop to do this. So I just set up a skeleton program here to take a single command line argument, which is the n I want. So a loop to do this, I would say, you know, int fac, I'll call it, equals 1. Let's say for int I equals 1, I is less than or equal to n I plus plus, and then I'll say fac times equals I. So this goes kind of in the reverse order. I do, instead of 5 times 4 times 3 times 2 times 1, factorial 5 would do 1 times 2 times 3 times 4 times 5. That's what this does here. And it accumulates that product. So let's just check to see, do we get the answer? So 5 factorial should be, that's 20 times 3, which is 60 times 2 is 120. So let's just build this. Let's build this. Let's see, what do we get for factorial 5? Okay, so 120, so that's good. So I wasn't lying to you. But there's a way to define this recursively as well. So let me abbreviate this a little bit, just to make it easier to write what I want to write here. Then I'll use a different name for the variable than the function name. Okay, so this is fac, so I got that. Make sure it still builds. Okay, so that's all right. Okay, so we could do it with a loop, but there's a way to do it without a loop by exploiting recursion, which is kind of interesting. You can write this as, okay, so n factorial is factorial of n. I was just writing the same thing. But the factorial of n can be written recursively in terms of the factorial of n minus 1. So what you say is the factorial of n is actually n times the factorial of n minus 1. So if you keep expanding this, you'll see that, well, that's equal to n times n minus 1 times factorial of n minus 2, which is equal to n times n minus 1 times n minus 2 times factorial of n minus 3. And so you'll keep going until this number is 1, and then it'll stop. So this actually will make for a much simpler implementation. What we say is if n is 1, so the factorial of 1 is 1. You just stop, return 1. Otherwise, return factorial, return n times the factorial of n minus 1. So we can do the same thing without a loop. Let me get rid of this loop actually. And now the code is very elegant and easy to look at. So let's just see, does that give us the same answer? Sure does. Okay, factorial 6 should be 6 times that, which is 720. All right, cool. So here is a recursive implementation of something we did in a loop a moment ago. Okay, there's another example I want to talk about of a sequence of numbers that we can compute easily with the recursive function. I'm going to show you how to do it with the loop, which is actually a little more painful than doing it recursively. But, okay, so here's the sequence. You may have seen it before, you may not have. The numbers go 1, 1, 2, 3, 5, 8, 13, 21, 34, and you keep going. So let me come up with an index for this. So this is, so Fibonacci of 1 is 1, Fibonacci of 2 is 1, Fibonacci of 3 is 2, Fibonacci of 4 is 3, Fibonacci of 5 is 5, Fibonacci of 6 is 8, Fibonacci of 7 is 13, Fibonacci of 8 is 21, Fibonacci of 9 is 34. Okay. So I'm just saying in particular I want fib of, for example, fib of 8 should be 21. Okay, so there it is. So if you haven't seen this before, I would encourage you to pause for a second and see if you can come up with a pattern of how I'm coming up with these numbers. So what's happening is every number is the sum of the two numbers before it, which, by the way, that's a recursive definition. Okay, so that's, you're going to implement that in a moment in C++. So anyway, 2 is 1 plus 1, 3 is 2 plus 1, 5 is 3 plus 2, 8 is 5 plus 3, 13 is 8 plus 5, and so on. Let me do this a more painful way that's a lot less natural using a loop. And then you'll do the easy way. Okay. So if I was going to do this using a loop, well, I have to remember, so I'll say the result, we'll start it off as 1. I have to remember the last number, and I also have to remember the second last number, right? So I start off, it's 1 and 1. I add those together, I get 2. So what I'll say is, I'll start at 3 actually. So for int I equals 3, I is less than or equal to n, I plus plus. So what I'll say is the result is the last plus the second to last thing I saw. Then I have to update the second to last thing I saw. I have to slide over by 1. I have to update that to be the last thing I saw. And then actually the last thing I saw for the next iteration is going to be what I just computed, the sum. Okay, so this is, I think this code is a little confusing. So you'll see that the recursive way is much more elegant, but let's just see, do I get the right sequence here? Okay, I do. So actually let me go up to 9, get all the way there to all that I had. Okay, so 1, 1, 2, 3, 5, 8, 13, 21, 34. So now I would like you to do this recursively, and that'll be the exercise.